Students, welcome to video class number 17, and in this session we are going to study about a steady state error that can come in a control system. For that, we first of all consider a canonical form of a closed loop control system as shown. Now you have this r of t as the input or the desired value or the set point, okay, and this is your c of t, which is your output, and this is b of t, which is the feedback signal. And what happens at the summer or at this point where this error or this output which is fed back is controlled is compared with this r of t, resulting in a signal called as e of t, and we call this e of t as the error signal in the time domain. Okay, error signal in time domain, right? Now that is actually the difference between the set point and the desired value and the obtained output. So this actually, the signal that comes at this point will give you whether the system is in control or not. Now as far as a control system is concerned, always this makes this error signal to be equal to 0. Now it will be always nice to transform this into frequency domain. So when transforming, you can represent this r of t as r of s, this as say some b of s, right, this as c of s, and this as e of s. Now let us try to write equation. What is e of s from the figure? Now e of s from the figure is given by r of s minus, right, r of s minus b of s. Now what is b of s? B of s is r of s minus h of s into c of s, right? But we know that this z of s is actually equal to r of s minus h of s into, what is the cs? Cs is actually e of s into g of s. Okay, you can write that as well this way, e of s into g of s, that is this signal gets multiplied by the g's, giving you gs. You can bring this term into the left hand side, so that you will get this e of s as 1 plus gshs, right? This is 1 plus gshs equal to r of s, right? Now what is this e of s? So this e of s is actually equal to r of s into 1 by 1 plus gshs. Okay, so this is actually the, what is this e of s? E of s is actually the frequency domain or s domain of the real error signal, okay, or the deviation of the output from the set point. That is what is called as error. So error refers to the deviation of the output from the desired value. Okay, now as far as a control system is concerned, the an accuracy of a control system is the faithful following of output, right? Faithful following of the output to the following of the output to the input, right? So this accuracy actually is determined by this error signal, right? Now what is actually the steady state? This is just the error signal, right? So this is the error signal that comes over here. So at any time you can have error signal, and the objective of such a control system is to make this error signal to 0. But now, as we have seen in our previous discussion, I will just draw the two responses that we studied for the first order system. Okay, so look at this. So you have a first order step response as shown and first order ramp response. Now, what does this do is this will make this e of s to 0, right? E of s to minimum. Now, we have seen that in our previous discussions that there are two responses. Responses can be classified as transient response and steady state response, right? Now, in the steady state response, for any control system, the desired thing is, it is the desirable condition is the error has to be zero. The idealistic condition is error has to be zero, or in a sense e of s has to be equal to zero. So definitely there will be some e of s as the control takes place, but the control action will be taking place in such a way that you need to make this e of s to zero at the steady state. And we have proved, in you can just refer those video, we have proved that the steady state error at this point is actually equal to, we have seen that the steady state error is zero. Now what do you mean by steady state? Once it reaches the steady state response, it is actually the deviation from the desired to the output. This is the output, and the output is more or less the same as the desired value. So we just found out the steady state error to be zero while we have discussed that. Now coming to this side, okay, coming to the first order, which is subjected to a ramp input. Actually you are supposed to get this output, but you're getting an output like this, meaning that we have seen that in the steady state there will be always a constant error of capital T. That is, the steady state error is equal to the time constant, which is not desired as far as a control system is concerned. Okay, so this is actually the what is called as a steady state error. Now let us see. So the expression for the error, this is actually error which is given by Rs by 1 plus GSHS. Now this error actually depends on two things. One is G of S, one is G of S H of S, okay, G of S into H of S, other one is the input. So the error actually depends on what? On one is the input, the other one is the function, the product of G of S into and H of S, and that is what is called as GS H of S is called as the open loop transfer function of a closed loop system. Do remember, it is not open loop, simply open loop transfer function. It is an open loop transfer function of a closed loop system. Okay, right? Now let me try to explain this steady state error in terms of the time domain signal. Now what is this? This is actually E of t. Okay, we know that this E of t is the difference of the set point and the output, right? Output. Okay, so the signal that is fed back. So based on that you will be having an error signal. Now initially for any control system there can be error. Now what does this control system do? This will make necessary corrections or necessary control action to the process so as to make this E of t to 0. Now when can you say that this E of s is controlled? The E of s is said to be controlled when the error becomes equal to 0, or you can say that once the system is switched on, you can say that the steady state error can be represented as limit t tending to infinity E of t is called as the steady state error in time domain, right? This is how you represent the steady state error in a time domain. That is the error as t tends to infinity. Look at this. We know that as the time increases there is an error from, this is the desired value, and this is the, say for example at t1, this is the output, and output has this much variation, this much deviation from the desired value. Now as time approaches, we have seen that in this case that it approaches to the desired and almost the error is 0. So in a sense you can say that the error that comes over here was this much at this point, while as time progresses this e of t almost goes to 0. So ideally speaking, this will be achieving its zero error only at t is equal to infinity. That's why it just written, we represent the steady state error as limit e of t as t tends to infinity. So this is the definition of a steady state error, and the steady state error is represented by ESS of t, meaning it is the steady state error. Okay, now this is nothing but this is limit t tends to infinity e of t, right? Now we know that when you take the Laplace transform of e of t, what you get is you will be getting e of s, and that is what is represented by this e of s. So this is actually the s domain of e of t, small e of t. Okay, s domain of e of t. So that means now if you know e of s, how will you find out the final value? So what is this? This is actually called as the final value of this function. This function e of t, the final value of that function, right? Okay, now final value of a time domain function. Now how to evaluate this? If you have this, you have something called as the final value theorem. You might be remembering in signals and systems we studied that final value theorem, which states that as limit t tends to infinity, e of t is actually equal to what? Actually equal to s into e of s, right? S into e of s as limit s tends to 0. I told you that there is an inverse at that time. To remember this, as t tends to infinity, when it comes to frequency domain, it has to tend to 0. Because there is an inverse relationship between time and frequency, and you need to apply this to s into e of s, and proof and all other stuffs we have seen in our signals and system course. Okay, so applying this, so if you have e of s, then how will you write this ESS of t? Now your new ESS of t in terms of this E of s will be equal to limit s tends to 0, right? S tends to 0, s into r of s into divided by what? By 1 plus gs hs. Okay, so this is actually your steady state response. This is very important. Okay, now look at this, the steady state error, sorry, it's not steady state response, steady state error. Now the steady state error depends on what? Depends on the input that you supply, and as well as GSHS, which I have already explained that to be the open loop transfer function of a closed loop system. Okay, okay, now we have seen that there are this error depends on, one is the input, the other one is the open loop closed loop transfer function input r of s, and open loop transfer function of a closed loop system g of s into s of s. So these are the two things that this error, steady state error depends. Okay, now the actual output of a control system, okay, that is in the practice, the actual output in a control system may be in some physical forms. I mean, say for example, if you're considering a mechanical system, the output may be a position or displacement, or we'll call that as a displacement, that is just a movement of something. Or it can be, the actual output may be a velocity, or it may be an acceleration, right? These are the actual output. Now this actual the displacement, so that is, if you consider a mechanical system, the output will be, the real output may be position, displacement, velocity, or acceleration. That is the actual output of a control system physically, that is in practice. Okay, now you can have a relationship with this, right? So this is x, this will be the derivative of x, dx by dt, this is d square x by dt square, and we have and it is seen that this all this actual output depends on the input as well, input of the type of the input. Now the output is a position or a displacement. It corresponds to unit step input. As velocity output is formed by you will realize a velocity output, and that is related to unit ramp input, and the acceleration that is related to unit parabolic input. Okay, that doesn't mean that it doesn't have any differential relationship between unit step and unit ramp, right? It's not in this way. Okay, you cannot differentiate unit to get unit ramp. No, there is no such relationship exist. Okay, you have the reverse relationship. But what I say is, when you give a unit step to a physical system, the output will be always a displacement. Okay, when you give a unit ramp, you can see the output we measure in a mechanical system will be a velocity, while when you give a unit parabolic input, you can realize the output to be an acceleration in a mechanical system. So in that context, we call this unit step as the displacement input, unit ramp as the velocity input, and unit parabola as acceleration input. Okay, so don't think that when you differentiate you will get unit ramp. That's wrong. That's the reverse will take place. When you differentiate unit ramp, you will get unit step. When you differentiate unit parabola, you will get unit ramp. There is no such relationship existing. But why it is called as a position velocity, and it is the big reason is, when you give the unit step input, when it comes to a mechanical system, the output will be in the form of a position or a displacement. When you give a unit ramp, it will be in the form of velocity. When you give a unit parabola, it will be in the form of acceleration. Okay, now so far we have seen this steady state error depends on the input, and you can have three classes of test input, step input, ramp input, and parabola. Based on that, you can have different physical outputs. Now another point, the second point which it depends is on the open loop transfer function of a closed loop system. Now a general open loop, we know that this GSHS is actually a polynomial, right? Is actually a polynomial. Now this can be, the generalized form can be written as, so this is of the form, say, some P of S to Q of S, or this can be the generalized open loop transfer function of a closed loop of a transfer function of a closed loop system is given by K into, say, 1 plus STA into 1 plus STB, okay, etc., and it goes on like this, divided by s raised to n into 1 plus st1 into 1 plus st2, etc., right? So now I'm going to let's see what are the terms that you can see inside this open loop transfer function. There is a constant term, and there is a factor of, okay, so this is a polynomial factor, or the factor of P of S, right? So when you take TA, it will be S plus 1 by TA. So that is why I told you this is a factor. So anyway, this is represented in this way: 1 plus STA, 1 plus STB, divided by S raised to N into 1 plus ST1. What is this? This is actually the factors of this Q of S, and N represents the type of the system, or it is defined as type of the system, right? Now what happens when you equate this P of S and Q of S to 0? Now we know that we'll be getting this as say, when you equate P of S to 0, what you get is, you will get the zeros of this transfer function, right? And the zeros of this equation will be, say, let us call it as Z1 will be minus 1 by TA, right? When you equate this to 0, you will get 1 plus STA is equal to 0. That means S is equal to minus 1 by TA, Z2 is equal to minus 1 by TB, and it goes on like that. So what are this? These are called as the zeros of this transfer function. While when you get Q of s to 0, you can see that I'll talk about, first of all, I'll talk about this. We'll come to that later. Okay, so you will be getting the poles as, say, P1 is equal to 1 by T1 plus minus 1 by T1, P2 is equal to minus 1 by T2, and so on, right? Now, what about this s raised to n? Now, when n is equal to 0, this s raised to 0 becomes 1. Okay. Now, what does this denote? This also represents a pole at the origin, right? Right? This is called as, this is actually the pole at the origin. This one is called as a pole at the origin, right? Now, based on the poles at the origin, system can be of different types. So that is why this n refers to the type of the system. When n is equal to 0, we call the system as a type 0 system. Okay, that's a type 0 system, meaning you don't have any pole at this origin. Okay, when you plot the pole 0 plot, you will be having numerous poles and zeros around, but you won't be having any pole at this origin. Now, what is n is equal to 1? N is equal to 1 refers to type 1 system, meaning you have, when you draw the S pole 0 plot, you can see that there is a single pole, that is S raised to 1. Okay. Now, what about a type 2 system? Type 2 system is a system where you have two poles. Okay, two poles with multiplicity, or poles with multiplicity 2, or we will call this as you have a multiple pole, meaning the pole is at the origin is equal to 2. So type refers to the number of poles residing at the origin. Okay, is it clear? Now we have seen now that steady state error is actually, it's an error calculated during the steady state period, right? Steady state period, right? So as I have shown in this figure, okay, so this is actually the steady state error, that is the deviation of this output from the desired during the, and we measure that during the steady state response. Okay, now because of the fact that we measure during the steady state period, this error is also called as the static error. Okay, now this static error, as I mentioned, that this static error depends on the input, right? Depends on the input function. Now the test input function that we consider will be unit step, unit ramp, and unit parabola. Don't forget the other name, that is the displacement input, velocity input, and the acceleration input. Okay, now for evaluating steady state error, we also define something called as the coefficient, which is called as the static error coefficient, and there are static error coefficient depends on the, it's related to the input. So we have studied that unit step input is also called as the positional input, right? Is also called as a positional input, and the error coefficient corresponding to that input we call as the static positional error coefficient. Static position error coefficient. Okay, and we usually denote that letter by K suffix P. Very important. Now next is second input is test input, we consider will be unit ramp input, and that is also called as the velocity input, right? The velocity input, that is the coefficient corresponding to this velocity input is called as the static velocity error coefficient, and usually represented by K suffix V. And finally the third input is unit parabolic input, unit parabolic input, and that is given by, that is also called as the acceleration input. Okay, that is also called as the acceleration input, and the coefficient corresponding to that is called as the static acceleration error coefficient, and it is denoted by the letter Ka. Okay, now what our aim is to represent the what we have already studied, that is ESS, right? Now ESS, we got a function like we got an expression like this. Now we are going to represent this ESS of t in terms of these coefficients Kp, Kv and Ka. So we are going to express this steady state error in terms of static error coefficients, or this Kp, Kv, Ka are called as the static error coefficients. Okay. Okay. Now let us see the static position error coefficient. I told you that static error coefficient is related to unit step input. So let's write this ESS. Now what is this ESS? ESS of t, or it is capital ESS of s, right? And it is nothing but limit s tends to s into, okay, I will rewrite it for you once again. We know that the steady state error is ESS of t is actually equal to limit s tends to infinity, sorry, s tends to 0 as s into ESS of s, right? Right. So what is this? This is actually limit s tends to 0 into s into, what is ESS of s? R of s divided by 1 plus GS HS, right? Okay, so this is the equation for the steady state error. ESS of t is given by this, okay, which we have already seen. Now using this equation, now I have told you that static position error coefficient is related to unit step. So what must be your R of t? R of t is actually your U of t unit step. So what must be your R of s? R of s is equal to 1 by s. Substituting that in this equation, you will get this as limit s tends to 0, s into, what is this? 1 by r, 1 by s into 1 by 1 plus gs hs, right? Right? So this s and s get cancelled. So this becomes limit s tends to 0 into 1 by 1 plus GSHS, okay, or this is a constant, so you can apply the limit only to this function. So in a sense, this will be 1 by 1 plus limit s tends to 0 GS HS, right? Limit s tends to 0 GS HS, or you can, so this is actually your steady state error, or you can call this as what? This as your Kp, right? So the steady state error due to okay, due to the positional input or associated with the step input is 1 by 1 plus Kp, where Kp is called as the static positional error coefficient. Okay, so this is your steady state error in terms of the positional error coefficient. Okay, static positional error coefficient. So therefore the steady state is 1 by 1 plus Kp. Okay, similarly we can find out the expression for static velocity error coefficient and the static acceleration error coefficient. Okay. Okay, now look at this. Second one is static velocity error coefficient. So we have seen this velocity error coefficient is related to the ramp input. Okay, so velocity input, which is given as R of t is equal to t. When you take the Laplace transform, you can write this as 1 by s square. Again, back to the steady state expression, which is given by limit s tends to 0 s into r of s into 1 by 1 plus GSHS. So when you put r of s to be 1 by s square, so you will get this as s divided by 1 divided by s square into 1 by 1 plus GSHS, right? Okay. Now what you will get is, so this s and s get cancelled, so this will be limit s tending to 0, right? S tending to 0 divided by 1 by, this is s plus s into GS HS, right? Okay, so this is s and s get cancelled, you have s and you are going to multiply this, so you will get like this. Now when you apply this limit as s tends to 0, this becomes 0. You cannot put s to 0 because we are not aware of g of s. G of s, h of s will also be a function. What's the basic thing, fundamental thing of applying limit? The limit has to be applied after every possible cancellation. So we do not know whether this s will get cancelled or not when we know this GSHS. So we cannot apply s to 0, but here s is allowed, so you can apply s. So this becomes 1 by limit s tends to 0 s into GSHS, right? 1 by 1 plus s into GS. Okay, now this is called as, okay, so this is called as, this limit s tends to 0 is called as what? Is called as your second coefficient, which we call as Kp. So the error coefficient, the ESS of t, is given by 1 by Kp, right? So this is the steady state error due to the ramp input, associated with the ramp input in terms of static velocity error coefficient. So similarly, now then the third step, you can also see, you can also find out that of the static acceleration error coefficient, okay. Now for the static acceleration error coefficient, the corresponding input will be r of t is equal to t square by 2, which is the parabolic input. Now we know that this r of s is going to be 1 by s cube. Okay. Now applying this in this equation, ESS is equal to limit s tends to 0 s into r of s, s into r of s. What is your r of s? It will be 1 by s cube, right? S cube into 1 by 1 plus GSHS. Okay, so this will get cancelled, so this becomes s square. So this becomes 1 by limit s tends to 0 s into 1 plus GSHS, right? Now expanding, you will get this as limit s tends to 0 into s plus s into GSHS. Okay, so this will be 0. So finally you will be getting this as 1 by what? Limit s tends to 0 s into GS s into this is s square, right? Sorry, s square. So this is s square. So this will be s square into GS into HS, right? So this is what is called as, so limit s tends to 0 s square into GS is what is called as Ka, the acceleration, static acceleration coefficient, or ESS of t. ESS of t is equal to 1 by Ka, or it is the steady state error associated with a parabolic input, and that is represented in terms of static acceleration coefficient. Okay, so this is it. So in this session, what we studied is, we have related the static error coefficient. As I mentioned earlier, the static error, steady state error, depends on the input as well as the open loop transfer function. Now, in this session, we have just seen the relationship. It's a relationship between the steady state error and the various inputs, test inputs that you apply. And so, in the next session, we are going to evaluate the steady state error based on the different types of open loop transfer function, because this steady state error depends on input as well as the open loop transfer function, and we will see in the next session how it is related to GSHS. Okay.